Okay, so this is OCR F324 Old Chemistry, the January 2011 question 6 for all you NMR fans out there. Normally I would advise you to read the full question, but actually today the stuff at the top is just giving you a little bit of background on this particular chemical the question is going to focus on. So we're being asked here to predict the splitting patterns in the proton NMR for this chemical here. The very first thing you should note is when there's a splitting pattern, it is all about the n+1 rule. And then crucially, because it's about protons, if you're given the skeletal formula, what you really want to do is actually include the protons. So I've drawn it out here so we can actually see the hydrogens, and I'm just going to use the same numbering that was used in the question itself. And what I've done is I've rotated it slightly so we can try and see the symmetry, because anytime we're using the n+1 rule, we are caring about equivalent hydrogens, and we are looking for where there's a line of symmetry to determine what is equivalent to each other. So there are 3 marks here, and for this one they're going to be about determining what each of the environments are and what the splitting is for each of them. Now, if you want to pause the video at this point and just try and spot what's equivalent, that's probably a good idea. So hopefully you have realized that this environment 2 is one environment. These ones here are a second, and because of the line of symmetry down the middle of the molecule, environments 4 and 6 are also equivalent. Now we don't need to include anything about the integrations, all we have to do is work out the splitting patterns. So the n+1 rule, n is the number of hydrogens and the key bit here is on adjacent carbons to the one that we are caring about. So if we start with environment 2, there are no adjacent carbons, so therefore there are no hydrogens on them. So for environment 2, that's simply going to be a singlet, because n equals 0. Right, moving on. Environments 4 and 6, they are equivalent, so there will be one peak area for these, but that's going to be split. So we have to look. This is not carbon, so we're going to ignore it. There is a carbon here, and there are 2 hydrogens on it. So here, n equals 2, so n+1 equals 3, and so for this, what we're going to see is a triplet, and that's these 2 things combined to give you a triplet. And then the very final part, environment 5, both of these carbons are adjacent. Each of them have 2 hydrogens, so here n equals 4, so n+1 equals 5, so what we get for this one is a quintet. Okay, 3 marks for each of the 3 different environments. On to part B. This time, however, it really is essential that you read the full question, because the key information for us here is it's an aromatic hydrocarbon. We've got the mass spec, and what you're looking for is the molecular ion peak. This is the highest number in here. So the M+, as we're going to call it, the molecular ion peak is at 106. Now I should let you know this question's out of 6, but actually there were 9 possible ways to get the mark. You've got 1 mark for getting the correct structure and up to 5 marks for the rest. But if you've got yourself 9 out of 6, that's a pretty good start to this. So M+ is 106. At this point, aromatic, C6H6 is the basic for benzene, has a mass of 78. So I'm now going to take my molecular ion and I'm going to subtract 78 from that to work out that there's a missing 28, and I'm missing off the screen. And from that 28, the most obvious thing it could be is 2 CH2s that are going to be in there. Now there's a few different ways we can fit them in, but if we look here as well, we have this fragment at 91, and 106 minus 91, well that's a difference of 15, which is the loss of CH3. So that is telling us that there is a methyl somewhere. They would have given you the mark for putting this as the loss of CH3, but you could also have put that 91 is C6 H4 CH3 plus. And I've got this because if there were two CH2s, then it makes me feel that actually there were two methyl groups attached to our aromatic ring. If I've lost one of them, I've still got one remaining and 4 standard hydrogens, remembering to put that plus there. Key thing therefore, we should at this point write in the molecular formula is C8H10, just trying to show everything that we possibly can from this. We're trying to pick up as many marks by showing all of our thinking. So all of this from the mass spec we know is C8H10. Now if we move down, it tells us there are 4 possible isomers, and we've got to use the spectra to identify which one it is. Now when you get these, what you want to be doing is referring to your data sheet and identifying, and you can write this down here, you can write it on the spectrum, but if you do, make sure you draw the examiner's attention to that. You want them to know that you know that this is a carbon bonded to a carbon, and you want them to know that this lot here are aromatic carbons. And then its key thing we're going to write out is that from the carbon 13 there are 5 environments. Now if you want to pause the video at this point and try and draw out the 4 possible isomers with the formula C8H10, that'd be a good one. I'm about to turn over and show you what they are. Okay, so we've now got, hopefully all of you got the 4 possible isomers. We've got 1, 2 and 3, which are with the 2 methyls added, or there was the potential for having an ethyl group on there. Now we're pretty certain it's not this one because we didn't see the evidence of losing 29 in the mass spec, and there was only 1 environment for carbon bonded to another carbon, whereas this one would have 2. In a moment I'm going to go through how many environments each of these would have. Probably again a good point to pause the video, use symmetry and try and work out how many different environments they all have. Okay, so hopefully you've had a good shot at this. Here the 2 methyls are equivalent, and the 2 aromatic carbons where the methyls are bonded to are also equivalent. There's a line of symmetry through the middle of this molecule that way, but there's also a line of symmetry going that way, and that means that those 4 are the same, and so we would expect 3 peaks for the carbon 13 NMR here because there are 3 environments. So we know it's not this one. Next, we have 1 line of symmetry here, which means that each side of the molecule is equivalent to its counterpart, but these ones are further away from the methyls than these ones, so they are not equivalent. And again, the carbons I've labelled as B have a methyl directly bonded to them, so they are not equivalent to these ones. So here we would have 4 peaks. Yet again, not our 1. We've already said we don't think this is the correct molecule because of the fact that we've got two different environments out here. But we'll keep going. The one with ethyl groups attached is going to be distinct from the rest. Apologies, because I've not drawn this to fully show it, but there would be a line of symmetry down the middle of the aromatic ring, which would give us these two as being equivalent. Because they are only one carbon away from the ethyl group, they are distinct from these ones, and then there's one final one there, so we've got 6 different peaks. Lastly, we have this molecule here, which is obviously going to be the correct one, and that's why I've left it till last, but hey, you know, got to find something to pass this lockdown. Those two are equivalent, they're the methyl groups. The two that the methyl groups are attached to on the aromatic ring are equivalent. There's no line of symmetry through the middle this way, so the top one is different from this, and we've lastly got these ones here. Thank you very much for watching.